All right, let's begin talking about L'Hopital's rule. So right away, let me get the pronunciation out of the way for us to be able to talk about this together. This is somebody's last name, and this person was a French mathematician. So by reading this, not the apostrophe is S at the end, this is a possessive in English. So L'Hopital. You pronounce it as Lo P Tal, like this. So this is the guy's last name, and the apostrophe S at the end is possessive because it's his rule, right? He wasn't the one who created the rule or invented it, but he was the person who wrote a very influential book where the rule was first found. As soon as Newton discovered calculus, his textbook was the first one that was very, very influential, very important. So we credit him this rule. Now, what is this rule and what does it help us resolve? Let's begin with the problem that it helps us solve. Whenever you have a limit of this format, f of x over g of x, and both f and g are going to infinity, then anything could happen here. For example, if I have something like this, then you can see that the top of this fraction is going to infinity because it's 2x and x is getting larger and larger. So this will be an infinity. And the bottom of this fraction is also infinity. So if you were to think about it, this is infinity divided by infinity, okay? But you can't say this is 1. You can't cancel the infinities out and say it equals 1, right? You can cancel the x's out to get 2 over 1, and now this is just 2. So you see they cannot cancel infinity with infinity. Infinity is not a number. When I write infinity over infinity, I do not mean that I'm dividing infinity by infinity because that's not a number and I can't really divide the two. What I'm saying is that I have two functions in a fraction, one at the numerator, one at the denominator, and they're both going to infinity. I don't know what the answer is. You see, infinity over infinity isn't always 1. For example, in the example I just showed you, that was 2, but it could be anything. If I can make it a 3 here, I can make an x squared. I can make an x squared over x. X goes to infinity, and that will be by canceling infinity. So infinity over infinity could be anything, including nothing, which is what I mean by equaling infinity. When I write that the limit of x when x goes to infinity equals infinity, that's not a number, right? So this limit right here does not exist, but it doesn't exist in a particular way. It goes all the way up forever and ever. So I just write that it equals infinity, but technically speaking, by the definition of existence of limit, that does not exist. So because infinity over infinity could be anything, including nothing, I give this type of expression a name. I say it's an indeterminate form of type infinity over infinity. Now, I, in particular, like to sometimes, not all the time, use quotations around the infinities here to really represent to the person who's reading that I know that I'm not dividing infinity by infinity, and that I know that this is not equal to 1. I know I can't just divide the two. Most of the time, if I write indeterminate form of type infinity over infinity, I'm okay not putting the quotations. But when I do not write all of this and just put the infinity over infinity, I'll most of the time put the quotations in there. So in here, I would likely put them. But on the top, I'm okay with you not writing the infinity over infinity. The second bullet point is saying that if you have both f going to 0 and g going to 0, then you have what's called an indeterminate form of type 0 over 0. As you know, you can't divide by 0, so I sometimes also do this. And the exact same thing happens. This is also what's called an indeterminate form, because I could just do the same here. I could just do x go to 0 instead and do 2x over x. So x, when I write 0 over 0, right, with quotations, I do not mean that I'm actually dividing 0 by 0. I mean that I have a function on the numerator, a function at the denominator, and that they're both going to 0. So I can cancel the x's here, and again, the limit of 2 when x goes to 0 is just 2. So 0 over 0 is not 1, right? 0 over 0 is not 1. 0 over 0 is an indetermination or an indeterminate form, and it could be anything, including nothing. Yeah. Limit could be 0, limit could be infinity, right? Or anything in between. So that's why it's also called an indeterminate form. So what L'Hopital's rule does is it helps us solve these. You've already known how to do some of these. For example, this one you've known how to do from previous videos that I have here on my channel. You know how to do this. And I'll give you a quick example. Here's this one. Here's this one. You have this limit, x goes to 3, of x squared minus 5x plus 6x minus 3, right? If I try to plug in 3, which by the way is what I always want to do when I'm solving for a limit, my number one goal, my ultimate goal, is to be able to just plug in the value. If I get a continuous function, I get to plug in the value of the x's approaching here at the bottom of the limit, and then say that that equals the final answer for the limit. But I can't do that, because if I do that right now, the bottom equals 0, and the top, if you do the math again, this will be, on the top here, it will be 9 minus 15 plus 6, which is exactly also 0. Right, so that is 0 over 0. Whenever I use 0 over 0, I do use quotation marks like this. Unless I also write the long phrase indeterminate form of type. And like I said, this could be anything, 0 over 0, including nothing. So I don't know what the answer is by just plugging in 3. I have to do something else. And from previous videos, as I've said, from basic limits, you know you can factor the top. X minus 2, x minus 3. Like so, to cancel x minus 3 out of the bottom, right? And then if you plug in 3, then that does end up being 3 minus 2, which is 1. So you have calculated your limit. Through factorization, you are able to get rid of this indeterminate form. Sometimes you say you're lifting the indeterminate form or lifting the indetermination, as if it's something hidden, something that's hiding, I'll say, the true result of the limit. This is like a curtain that's in front of the answer for the limit, and then by lifting it up, you're able to reveal that the correct answer is 3. So lifting the indetermination is a phrase I've heard people use. And factoring is one of the main ways that we know so far, how to determine or to lift an indetermination. Now, what if factoring is not an option? Yeah. What if factoring is not an option? So what we do is we use L'Hopital's rule. Let's talk about what L'Hopital's rule actually tells us. If you have a limit of this type, f over g, and the limit is one of these two indeterminate forms, infinity over infinity, or 0 over 0, so it's got to be one of these two, okay? Only if your limit is one of these two, and both f and g are differentiable, so that just means that you're able to take their derivatives at the points, at a like this, right? Then, or around a, I guess, then you can, to calculate your limits, just take both derivatives separately, okay? Just take them separately. That's not a quotient rule. Very, very important. Very common that students of mine will get confused and think that you're using quotient rule here, because this is a quotient. but you're not deriving the fraction. You're using L'Hopital's rule, which doesn't tell you to derive the fraction. It tells you to derive the top. The top is f prime, and then derive the bottom separately, the bottom becoming g prime. So as long as the limit exists, or if it equals infinity. So you're given the limit on the left. It's too hard. Maybe factoring is not easy. It doesn't work. And instead you decide to calculate the limit on the right. I'll try and explain to you why this is the case before we solve some examples. There are two things that that I like to tell my students about this. The first one is the idea, or I guess the philosophy behind this. When we start a calculus course, generally speaking, it's like you're climbing a very tall mountain. And right over there at the top, you have derivatives. Right? You want to get to the top so you can solve problems like the tangent line problem, like the velocity problem. And in order to do that, you have to climb this mountain. So you begin right here at the bottom, and then you got to climb the mountain to reach the top. And climbing the mountain is an arduous task. And to climb the mountain, you have to use limits. So in order to be able to solve problems with derivatives, you need limits, because you do the limit, the definition, f of x plus h minus f of x over h. You just climb up all the way to the peak to get to be able to solve problems with derivatives. And we've done that already in this course. Now at this point in this lecture, what we're doing is we're looking down. We're already at the peak. So we know we have derivatives already in our pocket. And now we see that some of the limits that we solved could be better solved using derivatives. So we're going full circle. By being at the top of the peak, I have a better view of the path that I took to get there. And I can see, I could have done this differently. I could have taken this path, or gone around this tree, or over this small hill or something. And now we're using derivatives to solve limits, okay? Which is, I think, something that helps students understand that you're not using the quotient rule. The second thing that I'll say now is, again, why this is the case. And the idea is to use linear approximations. And this is not really a proof. If you want to do f of x, g of x, this is like an engineer's proof or something. The idea is that this is if x is near a, right? Because x is going to a. You can use the linear approximation for f and for g at the top to get f of a plus f prime of a x minus a, and then g of a plus g prime of a x minus a, like this. So this will be the linear approximation for f at the top and the one for g at the bottom. Like so, right? And let's assume for a second that you had 0 over 0 to begin with. The other case can be proven slightly similarly. You can just do 1 over f or 1 over g divided by 1 over f like this. So let's forget about infinity over infinity for a second. Let's pretend that you have 0 over 0. Because if that's the case, when x goes to a, then f of a is going to be 0, g of a is going to be 0, right? So in fact, this is f prime of a, x minus a, g prime of a, x minus a. Remember, you want to plug in a the whole time, right, when you're calculating the limit, and you can't because you have 0 over 0 if you do. And so that's the 0 and that's the 0. The 0 for a for f and the 0 for g. So if there's 0, I can just not write them and get this. And next I get to eliminate these to just get f prime of a, g prime of a, right? Supposing that this fraction on the right exists. So this is the reason why it is, L'Hopital's rule is what it is. You get to derive the top, plug in a, derive the bottom, plug in a, separately, separate derivatives, and then that should give you the correct limit as long as the limit exists, or that it is infinity, right? again, this is for this blue proof, quote unquote, is for the 0 over 0 case, but the infinity over infinity case you can sort of do similar stuff by writing f over g as 1 over g over 1 over f. And when f goes to infinity, 1 over f is 0. When g goes to infinity, 1 over g is 0. So I can kind of do this and sort of repeat the same proof for this. And the derivatives kind of take care of each other, cancel each other out nicely. So I just want to give you an idea as to why this is the case. Okay, let's do a couple of examples, and hopefully that makes sense. Before that, I also wanted to show you this. So this on the left is a portrait of the Marquis de l'Hôpital. This is the person who wrote the book that I told you about at the beginning. And this on the right is the actual book. The book is called Analyse des Infiniment Petits. So analysis of small infinities. This is like a hugely influential and very important textbook on the right. It's actually kind of polemic. One of the Bernoulli brothers, Johann Bernoulli, he was actually claiming after L'Hôpital died that the book was essentially his, but nobody believed him. He was known to do this, to sort of try and take credit for other people's work. So because L'Hôpital, the guy on the left, the Marquis de l'Hôpital, you can see here the title as well on the right, that over here. Because he was kind of more charming and also more respected in terms of personality, then they believed him instead of believing Bernoulli, Johann Bernoulli. There's more than one Bernoulli, by the way, and I sometimes refer to them as the Bernoulli brothers because I have a hard time remembering which one is which a lot of the time. But that was Johann Bernoulli, the one that tried to claim L'Hôpital's work. And if I'm not mistaken, Johann Bernoulli also tried to claim some of his brother's work. So, kind of complicated. I'm working on my French, trying to maybe someday, one of the things I want to do after my French is good enough is to read this book. And this, by the way, all happened in the, I think, 17th century, so in the 1600s, mid to late 1600s. The book, I think, is from 1696, I think, or 1669. Let me double check. Yeah, I think so. 1696. And that was before Newton had already discovered calculus. And this was, like I said, a textbook that modeled the format of textbooks that come after. I imagine this is much better than the ones we use today, but I can't say for sure because I haven't read it yet. All right, now let's actually do examples. So let's do one of those at a time. Whenever I'm solving a L'Hôpital's rule problem, my number one goal is, again, to be able to plug in whatever x is going towards. So if you see this x to the power 9 divided by x to the power 9 minus 1 divided by x minus 1, what you want to do is really plug in 1, but you can't, right? You can't, because if you do plug in 1, you get 1 minus 1, so that would be 0, and then at the bottom you'd also get 0. So I always write this, and for my students, I also want you to write this so that when I read your solution, I know that you tried. I know that you checked that you can use L'Hôpital's rule, okay? You can't use it every time. You can only use it when you have 0 over 0 or infinity over infinity. So that was the first thing that I'll ask you to do. And then the second thing, when you use L'Hôpital's rule, I also want some indication. So you can write L'Hôpital here if you want. Or you can just write L' H if you want, to indicate that you've actually used the rule. And what does the rule say? The rule says that as long as I'm able to derive both functions and the limit on the right there exists, I can take the derivative of the top. So I'm going to take x to the power 9 minus 1 derivative, x minus 1 derivative, like so. this is 9x to the power 8 and 1. Not quotient rule again, just taking each derivative separately. And then that will be 1. I go back. Can I plug in 1 now? And yes, I can. I can plug in 1. I'm able to. And that is 9 when I plug in 1. So I've factored the limit. I could have factored this. This is not impossible to factor, but it is not as easy. Not everyone remembers how to do it. So L'Hopital's rule just makes it really, really easy to handle this. Okay, one more. Let's do B. Here, actually, factoring is not an option, you see. If I plug in 1, the natural log of 1 is 0. And 1 minus 1 is 0. So this will, again, be 0 over 0. So I use quotations to represent the fact that I've checked, that I know that I can't divide by 0, that I just try to plug in and I got this type of indeterminate form. And then I write this at the bottom. You can write the whole name, L'Hopital, or just this L''H to indicate that you're using L'Hopital's rule. I want you to indicate that to me always. And then use it. So take the derivative of the natural log and take the derivative of x minus 1 separately. Not quotient rule, just derive them separately. The top is 1 over x, the bottom is 1. And now can you plug in 1? Yes, you can, and the answer equals 1. So we've solved the problem. This is a perfectly acceptable solution to the problem. Let's go one more. Now x is going to infinity. That doesn't matter. L'Hopital's rule still applies as long as I get infinity over infinity. And do I, or 0 over 0, do I? This is e to the power of infinity. And again, this is not real math. This is BS math. What e to the power of infinity means is that I'm looking at the graph of e to the power x, and I'm looking at x values that are larger and larger and larger. And what y values, what happens to the y values? They also get larger and larger. So this is infinity at the top, like so. And at the bottom, I'm plugging in larger and larger x values, which then also, when squared, become larger and larger. Okay. So I've checked. Infinity over infinity is one allowed indeterminate form for L'Hopital's rule, and I use L'Hopital's rule. X goes to infinity. And take the derivative of the top, take the derivative of the bottom, and that's e to the power x at the top and 2x at the bottom. Now I go again, can I plug in x equal to infinity here, or make x larger and larger? If you try, you're going to see the exact same thing happen. E to the power of infinity again is going to be infinity, and 2 times infinity is going to be infinity one more time. And then I'm able to use L'Hopital's rule a second time. So that will be derivative of this, derivative of this. So that equals e to the x over 2. Now try and plug in infinity again. Will this be another indeterminate form? This will be, again, if I try quotes, this one will be infinity over 2. So when I have a very, very large number and I divide it by 2, it remains very, very large, right? So this is not going to be indeterminate. This is going to be equal to infinity. So the limit does not exist, but it doesn't exist in this particular way of getting larger and larger and larger. Key takeaways here. First, use L'Hopital's rule twice. That's pretty cool. Could happen. Could happen that you use it more than once, more than twice, even 3, 4 times if necessary. That was the first takeaway. The second is infinity over 2 is not indeterminate. I don't need L'Hopital's rule for that. In fact, I can't use it there. But infinity over 2 is just infinity. larger and larger number, just divide it by 2. It doesn't matter that you're dividing it by 2. You take like a million, a billion, a trillion, a quadrillion, you divide it by 2, it remains super large and it gets larger and larger every time. So it makes no difference. It's still infinity. So that was the second takeaway. The third takeaway is that this is going to happen every time. Every time I have an exponential function divided by any polynomial, x to any power, even to the power 50, you take the derivative of the top however many times you want, it remains e to the power x. But if you take the derivative of the bottom enough times, it's going to become 49, 48, 47, 46. It's going to come down. If you use L'Hopital's rule 50 times, then this is going to be e to the power infinity, e to the power x divided by some constant. So that's going to be infinity either way. At infinity, of course. Right? So this is really, again, BS math here, just trying to convey an idea. X goes to infinity, this happens. Exponential functions win the struggle with the bottom or the top, even if they are at the bottom. If you had this on the other way instead, you would have instead this going to 0, because the bottom's going to win. It's going to be much bigger. So the top and the bottom are sort of struggling, fighting each other, trying to pull the fraction into different directions. The bottom is getting bigger and bigger, trying to make the fraction 0. The top is getting bigger and bigger, trying to make the fraction infinity. And what I'm saying here is that infinity is winning the struggle. Or excuse me, that e, the exponential function, e to the power x, is winning the struggle against every exponential function. So if it's at the bottom, it makes it 0. If it's at the top, it makes it infinity. Right? Those are the 3 key takeaways. Now, this is the last example I want to solve with you today. As always, I try and plug it in. If I try to plug it in, I'll get tangent 0 minus 0. The tangent of 0 is 0, so that's 0. And 0 cubed at the bottom is 0. So this is 0 over 0, which is great for me, because I can use L'Hopital's rule now. I derive the top, and I'm going to skip some of the steps of writing the derivative and then calculating it next step. I'm just going to calculate it in the same step. So the derivative of tangent is going to be secant squared. The derivative of negative x is negative 1. And then the derivative of x cubed is 3x squared. Again, this is not the quotient rule. This is L'Hopital's rule. Just deriving the top and the bottom separately. Right, if I plug in x equals 0 again, this is what I always want to do. This is my thought process. I want to do secant squared of 0 minus 1. Secant of 0 is 1 of the cos over the cosine of 0. And the cosine of 0 is 1. So this is 1 minus 1, which is 0. And 3 times 0 squared is 0. So this is, again, 0 over 0. Which means that I, again, get to use L'Hopital's rule. Now the bottom is easy to derive. That's 6x. The top, not so much. The top is not so easy. The top requires me, well, the derivative of 1 is 0, doesn't matter. Derivative of 1 here is fine. Now, secant squared x, for me to derive it, I need to use the chain rule. I make u equal to secant of x. And then that will become 2u prime, like so. Chain rule here. If you've forgotten how the chain rule works, you have to go back and review it. I have a video for that. And then u is the secant. And then u prime is the derivative of secant, which is secant x tangent x. Right, so this becomes 2 secant squared x. There's 2 secants and tangent x. Okay. Move this out of the way here, put it here on the side. So 2 secant squared x tangent x goes all the way to 2 secant squared x. And I don't need the 0. Tangent x. Okay. I've used L'Hopital's rule twice at this point. Also box this, so No, it's not part of the solution. And again, I want to plug it in, but you see the tangent of x here. One more time. Another tangent of x. Yeah. Another time. And we know the tangent of 0, 0. So this is, again, going to be 0 over 0. It's crazy. Yeah, it's the third time I'm allowed to use L'Hopital's rule. As long as I'm done with this process at some point, all of my calculations will be correct. If I'm never done, then they're all going to be wrong. Because one of the conditions for L'Hopital's rule is that the limit on the right existed. So I have to make sure that the end here, the final answer, gives me something. X equals 0. Derive the top is easy. That's 6. Great. I no longer have a division by 0. So I'll be done at this point. Whatever happens at the top, right? If I have a limit of 0, right, that'll be fine because it'll be 0 over 6. 0 over 6 is not in a determinate form. 0 is divisible by 6. The answer is just going to be 0. So it doesn't matter what the answer is exactly, more or less, right? As long as I do get an answer, a limit that does exist. All right. So now I have products that I need to take the derivative of. So it will be a product rule. So the derivative of the first, deriving secant squared. I already did it. Did it in the previous step with the chain rule right here. You see that? That's 2 secant squared tangent x on the left. So it's going to be 2 times 2 secant squared x tangent x. Maybe I'm out of space. Zoom in a bit, make it a little smaller. Just make sure it all fits. Derivative of the first times the second plus the first times the derivative of the second. And now deriving tangent is easy. That's secant squared. Secant squared x. And of course I can reorganize and do everything that I need. But as soon as I'm done with the derivatives, I can try and plug in x again. When I plug in x equals 0, tangent 0 remains, so all of this is going to be 0. But thankfully, this is not going to be 0. Secant of 0 is 1, because secant is 1 over cosine, and the cosine of 0 is 1. So all of this is going to equal 1. Well, with the 2 there, 2 times 1, you see? So the answer here is going to be 0 plus 2 over 6. So it's going to be 2 over 6, which is going to be a third. So finally, we're done. L'Hopital's rule allowed us to get out of this pickle. Can you just stop and go back to the beginning and imagine factoring this tangent? How do you factor this tangent in a way that allows you to cancel this with x cubed? Yeah, I don't really know. So you end up with 1/3 by using L'Hopital's rule. So I hope that made sense.